Have you ever wondered why some knots hold tight while others easily unravel? Today we dive into the fascinating world of knot theory, a unique branch of mathematics that digs deep into the mysteries of knots. But hold on, we're not talking about the knots you tie on your shoelaces or the ones that make your headphone wires a tangled mess. We're exploring knots in three-dimensional space, knots that exist beyond our everyday perception. Imagine a knot so complex that it exists in a space you can't even see. And while it might seem like an abstract concept, it's far from just mathematical musing. These knots have practical applications in fields as diverse as physics, where they help us understand the fundamental fabric of the universe, to biology, helping us decode the complex structures of DNA, and even in computer science, playing a key role in cryptography and data security. Knots, it seems, are a lot more complex and interesting than they first appear. Remember, in knot theory, a knot is a loop in three-dimensional space that doesn't intersect itself. Now imagine that knot as a rubber band. It can be twisted, turned, and stretched in all sorts of ways, but you can't break it apart or glue the ends together. That's the essence of knot theory. This theory delves into the fascinating world of knot equivalence. Now what's that, you might ask? Well, simply put, two knots are equivalent if you can transform one into the other without resorting to scissors or glue. Twist it, stretch it, bend it all you like, as long as you don't break that loop, the knots are equivalent. Think of it as a game of shape-shifting. You start with one shape, and through a series of twists and turns, you end up with another. But here's the catch. They're still the same knot despite their different appearances. Now let's talk about the unknot. It's the simplest of knots, just a plain old loop. But don't let its simplicity fool you. You see, one of the major questions in knot theory is determining whether a given knot is an unknot. Sounds simple enough, right? But remember, we're dealing with three-dimensional space here, and the knot can be twisted and turned in countless ways. What may appear as a complex tangle could be, with the right series of twists and turns, just a simple loop. And that, my friends, is the challenge of the unknot. Knot theory is a world where everything hangs on a twist, a turn, a stretch. It's a world where appearances can be deceiving, where a simple loop can hide a maze of complexity, and where a tangled mess can turn out to be the simplest of knots. It's a world where the rules of the game are as flexible as a rubber band, and where the goal is not to untie the knot, but to understand its twists and turns. It's a world where a simple twist or turn can change everything. Now you might be thinking, why should I care about knot theory? Well, you'd be surprised. See, knots are not just about tying your shoelaces or securing a boat to a dock. Knot theory has real-world applications that are far-reaching and incredibly important. Let's take biology, for example. Scientists use knot theory to study the complex structures of DNA and proteins, helping them understand the very building blocks of life itself. Then there's quantum physics, a field where knots play a crucial role. The peculiar properties of knots help physicists unravel the mysteries of the quantum world. And let's not forget about computer science. Knot theory is used in creating secure cryptographic systems, ensuring that our online information remains safe and secure. So the next time you tie your shoelaces, remember there's a whole world of mathematics underpinning that simple act. So, we've unraveled the mysteries of knot theory, but what are the key takeaways? Firstly, knot theory is a remarkable branch of mathematics. It plunges us deep into the world of knots in three-dimensional space, twisting our perception of the physical world. It's not just about tangling and untangling strings, but a study of how these knots can be transformed without being cut or glued. Central to this theory is the concept of knot equivalence. This idea questions whether two knots can be transformed into each other without breaking. Alongside this, we have the fascinating question of determining an unknot, a loop that can be untwisted into a simple circle. Despite its seemingly abstract nature, knot theory ties up neatly with the real world. It threads its way into various fields, from DNA research to computer science, and even to the study of black holes. Knot theory, then, is a fascinating blend of complexity and simplicity, of abstract ideas and practical applications. It's much more than just knots in a string.